A very simple formulation of general relativity is that matter tells space-time how to curve, and space-time tells matter how to move. So the motion of the particles take place in a curved space-time, and the motion of these particles in fact is determined by the space-time, but how to curve is there to the space-time by the matter. And mathematically, these are the so-called Einstein field equations involving a lot of geometrical components I will not discuss at all. Now, of course, many people believe that what I have said to you are just the hallucinations of a man mind. So in order to accept all these mad ideas, you need a lot of experimental observational confirmation. And it turns out that presently the general theory of relativity is one of the best tested physical theory ever existing. There are a very large number of tests who have proven that in fact all these predictions are correct. And the first confirmation of the general relativity was the so-called deflection of light by the sun. So because of the fact that the geometry near the sun is different from the flat one, so we have a strong curvature near the sun, the light from distant sources in fact will move on a more curved trajectory than in the Newtonian case. Even in the Newtonian case, we accept that the photon has some mass, and it is attracted gravitationally to the sun. The deflection angle turns to be incorrect. But Einstein predicted the correct angle, and this has been also measured, and it is also measured many times. The second very important confirmation of the theory of the relativity is the so-called perihelion precession of the planet Mercury, which is a big mystery for Newtonian mechanics. Because in Newtonian mechanics, as we have studied, the orbits of the planets are constant, they are not changing. So according to the Newtonian dynamics, the planets move on elliptical orbits, and these orbits, they do not change. However, the observations have shown that in the case of the Mercury, this orbit is precessed. It is in fact rotating. So if, let's say, 100 years ago was somewhere here, today there is a small rotation of this orbit, of course not as big as in this figure. And this again is a mystery for Newtonian mechanics. There is no explanation for this effect, and in fact the general theory of relativity gives a very good, the most perfect estimation of the precession angle, which is 42 seconds per century. And we have also the black holes, which are other very interesting predictions of Einstein general relativity, but I will not discuss them. Because very briefly I will introduce to you now what is called relativistic cosmology. So Einstein is not only the father of the theory of the relativity, he is also the father of the theoretical cosmology. Because in 1917, he proposed the first scientific cosmological model. And this model has a very interesting history. So initially, Einstein thought that the universe should have been static, unchanged, because in 1917 this was the observational situation. It will take around 15 years for Hubble to discover the expansion of the universe. So in 1917, the universe was thought to be static. So Einstein built, in fact, tried to build a model for a static universe. But it turns out that this model was unstable. No matter how Einstein chose the geometry, the pressure, the density, this model was always I may say, in motion, it was dynamic. It was impossible to build a static model of the universe using the initial equations Einstein has proposed. So he modified these equations by introducing what is now called the cosmological constant. And this constant acted in Einstein's original model as a kind of anti-gravitational effect. So the cosmological constant, in fact, made somehow the universe stable, made the universe static and stable. It is, in fact, a kind of anti-gravity effect. And with this constant, Einstein's universe became stable. However, 5 years after Einstein's work, a Russian mathematician, in fact, has shown that Einstein's equations naturally describe an expanding universe. So in a natural way, in fact, Einstein's equations can describe an expanding universe, and also these equations show that at the beginning of the universe it was a kind of singular state. And this work was done in 1922 by Einstein. It is also very interesting history because Einstein was the referee of Friedman's papers and he rejected them, initially pointing that Friedman had made a calculational mistake. And then it was shown that in fact Einstein was the one who made the mistake, and finally he accepted these papers, but he wrote in the report that anyway these results are purely mathematical and they do not have any physical relevance. But they may mathematically be correct, or physically they are irrelevant. So by 1922, it was known that in fact the universe may be expanding in the theoretical framework of general relativity. So these are the equations of general relativity, and these are the so-called Friedman equations, which are today the theoretical basis of cosmology. So everything about cosmology is contained in these equations, where this R is the scale factor describing the expansion of the universe, this is the density, this is the pressure, and this is the coefficient K, which is related to the geometry. What kind of geometry we have in the universe. Now, technically, what Einstein has done in his modification of general relativity was to introduce this new term, which is called the cosmological constant. So initially, Einstein proposed only these equations with this term. But in 1917, he has observed that in order to have a static universe, we have to introduce this cosmological constant. This cosmological constant can also be introduced in Friedman's equations, so the basic equations of cosmology that are used today are in fact these equations. So everything we know today about cosmology is contained in these two very simple equations. One should add to them only one more equation, which is an equation of state relating to the pressure and the density. So cosmology is technically a rather simple science because it is based on only two equations, and with these two equations you can explain everything it is observed in the universe. So after Einstein learned about Hubble's discovery, probably he was not very happy because he declared that the introduction of light, so pushing the universe to be stable and not to expand, was the biggest blunder of his life. And indeed, if Einstein would have not introduced the cosmological constant, he would have made one of the greatest predictions in the history of science, the expansion of the universe.